So as it is clear from the picture, uh, if you want to show that this excursion is an IID in some sense, exactly in what sense it has to be made clear later, important quantities are these return times, because that's when the excursion ends. Like first excursion ends when the Markov chain returns first time to 0. Similarly, the second excursion ends when after the first excursion, when the Markov chain goes out from this state 0, when again it returns to 0, and so on. Okay? So this end of each excursion is essentially each of the return times, the first return time, second return time, and so on. And these are random quantities which are going to be extremely important. So let's start from there. Okay, that's our first quantity to define. Namely, suppose you have a Markov chain on S with transition matrix P. So in this case, initial distribution will fix it to be a one state. So we'll fix a state I and assume that the Markov chain starts at I. So this is a mistake. This should be I. This is a typo. Okay? So we start the Markov chain at I. So we define tau I 0 to be 0. So the Markov chain starts at I. So the 0th return time. So this is the 0th return time to I, which is 0. Now what is the first return time to I? So the first return time is the first time starting from 1, xm becomes I. Okay, this is the first return time to I. So since we start the Markov chain at I, again, this is, as I said, this is a typo, it should be I. So since it starts at I, this is called the return time. This is the first time you are returning to your initial state. Now, of course, as before, if the Markov chain never returns to I at all, then this would be defined to be infinity. So infimum of any empty set is infinity. So with that convention in mind. The second return time would be on the event. So we'll define the second return time only on the event when the first return has already happened. In other words, tau I1 is finite. So after some finite amount of time, the Markov chain has returned to its initial state, which is I. Then we define the second return time as the first time strictly after the first time strictly after the first return time when the Markov chain returns to I. So that's the second return time. And we don't define it at all when the first return time is infinity. Now you would say, okay, this is not even well defined. It is true that it is not well defined, but we are not going to bother about that. We are only going to define this only on that part of the sample space where this is finite. So in other words, if this is infinite, if tau I1 is infinite, the first return time is infinite, then second return time is not even defined. Okay. When the first return time is finite, this is well defined. Now this can still be infinity because after returning for the first time, it may so happen that the Markov chain never returns for the second time. So therefore, this can still be infinity. It's possible. Okay. And we can go on. So we can continue this way. On the event that the first return time is finite, second return time is finite, all the way up to the nth return time is finite. Okay. On this event, we define the n plus 1th return time to I as first time strictly after the nth return time, the Markov chain becomes I again. Okay. Now again, even though these are finite, this can still be infinite because it may so happen that the Markov chain returns to its initial state exactly in number of times. So this becomes still infinite. It's possible. Again, as I would comment that this is not even defined when one of them becomes infinity. In fact, if tau 2 say becomes infinity, then tau 3 onwards are not even defined. So what I am saying here is that all of them are well defined and they're all finite. Okay, when I write like this, it means that all of them are well defined and all of them are finite. What we will eventually do will actually condition on this event. So therefore, whatever I am saying, it will not make sense at all right now. You may think, okay, things are not even well defined. How are you going to talk about these things? Don't worry about such things. That technical part would be taken care of by a suitable conditioning. Okay. Okay, so let's now go back to our picture and see what are these objects. So in this example, remember, we went to 1 and then came back to 0 immediately. That was our first excursion. Second excursion was then 1 to 1, then 2, then 1, then came back to 0. Okay. So in this case, of course, our I is 0. So our Markov chain starts at 0. So therefore, I is 0. And the first return time is 2. That's when the Markov chain first time comes to 0, after starting from 0, of course. And then after 2, it comes back first time to 0 at 6. So therefore, the second return time is 6. So in other words, excursions are therefore going to be the Markov chain seen in between these return times. Okay. Even before we define that, let's try to state at least what we are trying to show. We will show that the successive excursions between visits to the state I are IID. Now, of course, you would ask, it's, return times are not even well defined. What do you mean by IID? Okay, it would be IID under some conditional probability so that the return times are well defined. Okay, we'll see when the statement comes. But before that, let's try to define one more quantity. Define alpha 0 to be 0. Alpha 1 to be the first return time to 1. Alpha 2 to be the difference between the second return time and the first return time. How long it takes after the first return time for the Markov chain to come back to 0. So in other words, if you set your clock at 0 at the first return time, and then in your new clock, how much time it would need for the Markov chain to come back again to its initial state. That's alpha 2. Of course, alpha 2 won't be well defined unless the second return time is so. Therefore, we'll define alpha 2 only on the event that the first return time is finite. Okay? If the first return time is not finite, we don't define alpha 2 at all. And we go on doing this. We can then define the third return time and so on. It's clear that these are nothing but the lengths of the excursions. Each alpha k is just length of the kth excursion between visits to I. So alpha 2 is the length of the second excursion. How long it takes to come back to the second time to I right after the first time. Okay, so it's the length of the excursion. So in this example, we had taken I to be equal to 0. Our first return time was 2. So this is first return time. Second return time was 6. Okay. First excursion length is therefore 2. 1, 2. So this is 2. That's your alpha 1. Second excursion length is 1, 2, 3, 4. It's 6 minus 2. So therefore it's 4. So in this case, alpha 1 is 2 and alpha 2 is 4. Okay. So the first excursion length is 2. So this is 2. This length is 2. So this is alpha 1. This length is 4. This is alpha 2. and so on. I can also have more excursions and define it. The mth excursion between visits to I will be the block you start it after it has come back to I m minus 1th time. After that you start and then go on all the way up to it comes back to the mth time to I. Now, of course, this is going to be well defined provided the first return time, second return time, all the way up to the m minus 1th return time are all well defined and finite. I could have just said the m minus 1th return time is well defined and is finite, because that would automatically incorporate that the previous return times are well defined and finite. Okay. Otherwise, this won't be well defined. But anyway, I always prefer to write like this. So on this event, this is the excursion. If this event doesn't happen, we don't even have any excursion. We don't even define the excursion. So this is, as I said, this is the first excursion in this example, and this is the second excursion. So between visits to 0, of course, I should have mentioned that because it starts at 0. The first excursion therefore would be 1. First it goes to 1 and then 0. The first excursion will be denoted by 1, 0. Okay. After the first excursion is finished, which is this first return has happened, the first return time is 2, then it goes to 1, and then 2, then 1, then 0. And the second excursion therefore is 1, 2, 1, 0. So that's the second excursion. And so on. Okay, we can have more excursions. And this is how we'll define it.